Good morning. We're going to get started, and first thing I'll mention is, will the projector turn off again? I would say absolutely yes, but the latest theory, and this is my theory, and it seems to be somewhat interested in the AV group, is that when they rewired the building to put in all these motion detectors to control lighting in the classrooms, that I think that projector might be on that circuit. And we are pretty quiet when we're in here, and it has a timer associated with it in motion, and that's what I'm thinking. I mean, it seems like that because it is so, it happens generally when we're all very quiet, right? It just sort of, all of a sudden, it's shutting off, and I know that's the way power-controlled lighting can work too, unless you move, and I don't think the projector would restart because it has to be restarted. It shouldn't be on that outlet is my feeling. So, okay. So two of you are here. I thought I'd just show this page, and I don't know whether this page has been helpful, but I've been putting this up. I don't know whether either of you have looked at it. It's the histograms of the homeworks. It's not particularly exciting because there's not that many people in the class, but as it stands right now, this is a composite, and it has to do with the fact that, you know, one person in the class only turned in set number 1 and never turned in set number 2, and that's why there's that low point down there. So if you look at the 4 most active people in the class, you can see what we've got in terms of those top 4 ticks. And everybody, and this is normalizing everything out of 100. So the bottom line is, with one exception, and that person has an issue that we talked about, and that I think is going to be resolved, I think everybody's doing fine on the homework. I'm happy with it. What I will do, though, and what this histogram thing is all about, too, is that I will put the exam up in a similar fashion, and then I will do predicted, you know, grades and stuff like that. I will merge in the homework component as it continues to evolve with more and more papers getting turned in, and then I will merge in the exam 1, and I will proportionalize them the way they get proportionalized in the syllabus, like, what is it, 25% for the homework, and I think it's 15% for each exam, so I'll put both of those numbers in at that weighting, but then I'll divide by the sum of those 2 weights so that it comes back to 100%. And you'll just be able to see what's going on throughout the semester. I know what's the teaching management system that the campus has something maybe fancier, but, you know, I don't do that, so I don't. If I was still a regular faculty member, I'd probably be talked to for not participating in Canvas, but I just don't do it. I mean, those of you that have had a Canvas class, they have a thing you can see your grades in, right? In the olden days, it wasn't like that. I mean, when my sons were in school, we had something similar, and it was like too much information. I mean, but I guess parents, it's kind of like something I think people have grown up with now, so they expect all that. So we will bounce into looking at the old exams at the end of the period as a review. Meantime, though, let's go over to where we were before. I will be showing you some demos of sampling theory, GUI slider type stuff, animating sampling theory. We'll look at some catalog stuff for A to Ds and D to As a little bit, and then we'll just keep moving on and perhaps get into the multi-rate side of things. So we looked at this picture last week. This is sort of a top-level view, and one of the things that I forgot to say because it was near the end of the class period is this looks like a system that goes all the way through from analog to analog. And I'll be calling that an A to D, D to A system. And there's a block diagram, a simplified block diagram that the book uses, and I have in the notes. But a system doesn't have to be like that. I mean, if you listen to music on an audio device or on your cell phone it's the back half of this. It's the DSP processor played out through the D to A and then the filter. And if it's a recording system, then it's the front half of it. So it doesn't always have to be a through system in this exact fashion. In most radio applications, it is a transceiver, so it's both a receiver, the receive side or input side, and then the transmit side, but they're generally in two different modes of operation. Like in the SATCOM stuff that I've been working on, it's the receive path is one and one frequency, RF frequency, and that's bringing stuff into the box, and then there's an uplink frequency that goes back to the base station or goes back to the satellite, and that's on a different frequency. So it's not quite a through system. This is more descriptive of how you might have real-time audio enhancement, let's say, for a through system. So we started to talk about periodic sampling last time, and it's basically taking the analog signal that we're familiar with, and we're going back to this notation that I had at the very beginning of the class where we said a continuous time signal would frequently have the subscript C to mean continuous, and then the parentheses denote the fact that it's a continuous time signal, and we're taking samples of it. So N times capital T, and we'll be talking about, sampling period and the fact that the sampling rate is 1 over the sampling period. That'll always come into play in everything that we do in this chapter and pretty much for the rest of the semester, because every time we work with discrete time systems now, there's going to be a homework problem or something that will relate it to the analog world through a sampling type system. And this is the way all the books problems are set up. They will show C to D, meaning continuous to discrete. We'll see in a few moments here we'll have a D to C to be discrete to continuous. But if you want to think of that as an analog to digital converter or ADC, and you want to think of the opposite, the D to C, of being a digital to analog converter, that's fine, because that's what the real components look like. So right now our C to D converter is taking an analog signal over here, and it's first converting it to an impulse train by following the sampling operation. So the sampling is just modeled for mathematics as a signal S, and S means a switching or ideal impulse train in this case. So we're just coming along, multiplying the analog waveform by a uniform space sequence of deltas to take samples of the waveform. The actual analog to digital converter is a little bit different because it might have a sample and hold and some other pre-processing in it. But for the math modeling side of things, and that's what we're interested in, is how do we get a representation for the sampled signal from the analog signal in both time and frequency. On the time domain side, it's just multiplying the two together, or it turns out being this guy right here. The analog signal is the little XC and then the impulse train. And if you want to look at a picture, the impulse train would be what's on the left, and that's fictional, but it's just a math representation again, because this happens inside the A to D, how this actually functions, and that gets studied a little bit more towards the end of this chapter. But what we want to be able to say is that it's a delta function in the continuous time domain at the input after the sampler, but in reality we just care about the sample value, which is the amplitude on an integer versus an integer axis. So it's just going to be the standard discrete time plot, the stem function. That's what the input looks like after sampling. So now we have to go back to a traditional analysis to get the frequency domain view. So here it's just looking at the frequency domain representation of a sampled analog signal. There's nothing digital in here. There's no discrete anything. And the book's notation is capital omega is the frequency domain in radians per second, and the normalized digital frequency will just be f, which would be omega divided by 2 pi. We don't have that yet, but it's coming up. So f will be in hertz, omega is in radians per second. Actually, that's not quite as good as it should be. It's a little bit confusing, and I'm not consistent on this, and the book does not really even talk about it too much. But if you take the analog frequency and divide it by fs, then you get the normalized frequency in the discrete time system in samples per, in hertz per sample. That doesn't appear in this blue box, though, but this blue box is something you would have seen in another earlier signals and systems class. I'm just going to work through it again now. It's telling us how we can get the spectrum of the sampled analog waveform, this guy right here, and we get that because we have, in our notation over here, we have this product x of t times s of t. So in the frequency domain, that will be a convolution of the spectra, or the Fourier transforms, of those individual time domain signals. Now, at this point in the class, though, I haven't really introduced what the Fourier transform in the continuous time domain looks like. So I put that on this page, just a review of the continuous time Fourier transforms using radians per second rather than hertz, and that's going to vary all over the map depending upon where you took your classes, what books you used, and things like that. But when I teach communications theory related classes, I use f for the frequency variable in the Fourier transform, whereas a lot of other DSP books will use radians per second, and that's what this book is using. So this just establishes that notation. We'd have a different Fourier transform setup if we were using f rather than capital omega, and it would just be 2 pi times f in place of omega. But this is what we need for this book, so this is why this review is designed to look at the omega domain Fourier transform. And a characteristic of the omega domain Fourier transform pair is that when you inverse transform, you have to divide by 2 pi. Do you happen to remember, this is just a sanity check, if you were doing F domain, or in hertz domain, you don't have a 2 pi in there. You go backwards and forwards from time and frequency in hertz without a scaling factor like that. And I don't quite have Com1's website put together. I'm building it in the background. It was on my old website, but it'll be there fairly soon along with the lab, because that's stuff I want to get done for next semester, since there's still no new faculty member, and that person is going to be hired hopefully this semester. I really don't know. But so we also need the rectangular pulse shape, and this is just the definition of this capital pi function. It could be time or it could be frequency. We'll be first seeing it in frequency for an ideal low-pass filter, but this is just the definition of it. And also just recalling the sinc function once again, and then some Fourier transform pairs. So the Fourier transform pairs that are of interest to us is if we have multiplication in the time domain, we have convolution in the frequency domain, and this 1 over 2 pi just shows up because of the omega domain transform. And then the other thing that we use, so we're homing in on this right here, and one of the waveforms is the S of t, which is the impulse train of ideal delta functions, and that's here on the left, and in the frequency domain it looks like this. So it's delta of omega minus n times omega naught, where omega naught is 2 pi over capital T, is substitution right here. So that comes together right here, and it comes together in a memorable way in that when you go to the capital omega domain, you end up with a 1 over T from that impulse train, and then you end up with the spectrum in the omega domain of the underlying analog signal just being replicated up and down the frequency axis. So it's just all the frequency shifts by the sampling frequency in radians per second. So if we were to start with an analog signal with band-limited spectra, which is what this is showing you, this is pretty much a standard textbook example of using a triangle shape. It's band-limited to capital omega n radians per second. So there's its Fourier transform, and then when we sample it with an ideal sampler, and again, notice capital omega, so we're still in the continuous time domain, it just replicates that spectrum at all multiples of omega sub s up and down the frequency axis. That is the net result of sampling a signal. It produces those spectral images. And this is showing you for omega sub n, well, omega sub s being greater than twice the highest frequency, which is omega n, and this would be said to be obeying the Nyquist low-pass sampling theorem. We're sampling at a high enough frequency that those triangles don't overlap. If we sample at a lower frequency, less than 2 omega n, then we get the overlapping, and that's referred to as aliasing. It's saying that we're not sampling high enough, so frequency content from the translates is overlapping the so-called baseband spectral shape, which is this piece right in here. It's corrupting it with the fold-over or the alias, and our technique for recovering is not going to work in that case. The technique for recovering is to follow this system with a low-pass filter, and the low-pass filter is supposed to be plucking out the baseband spectrum. Whereas up here, if I repeat that operation and put the low-pass filter in, it can perfectly pull it out. And that's the whole notion behind recovery in a sampled signal. Now, right now, just starting with the analog system idea, it seems like nonsense. I sample a signal, I get all the spectral images, and then I'm going to low-pass filter to get it back again. That's not really our game, though. Our game is to sample it, convert it into a discrete time waveform, take it all the way through a system, and then go back to analog again. Otherwise, we're just doing a simple math exercise, right? But it's just telling you that samples of an analog signal, as long as it's band limited, we can reconstruct from the samples. Does that sound good? I'm thinking back to something that I could use as an example where you experienced this if you were traveling by an airplane, but it's been such a long time that they don't do that anymore. I'll maybe just check and see if your memory might recall. Do you ever remember being in an airplane where the earphones they gave you to listen to music or the cockpit were these sound tubes? Does anybody remember that? You do, okay. So there they were using a time division multiplexing system, and the sound tubes was just simply a way so that the actual emitter was in the armrest, and the sound would go through the tube, and then it would get into your ear. But the system on the airplane, with the knob usually on the seat arm handle, was multiplexing between different channels. So if you could envision, these were our impulse train samples, and they would put other samples from other sources interleaved with this. And your channel would just select off the channel you want, and if you rotated the knob to pick a different channel, it would slide over and pluck out the samples, and then they were reconstructed with a low-pass filter, all in the analog domain, from a switched signal system. Does that sound crude? I mean, it was the beginning of the way things were done. Of course, now we know it's done a lot differently, but that was pretty direct to the metal DSP switch signal stuff, or switch, all analog sampling stuff. So the way an ideal recovery system, exact recovery, would work, if we start out with the analog signal, we sample it, so we get these images in there, and then we recover it by putting the filter around it like I was just showing, and then we get it back again. And an important point to note, because this is something that you'll have to keep track of when you work homework problems, is that because of the 1/T that's introduced in sampling, and the way you can think of that 1/T is when we sample the signal, we're getting less energy because we're only taking samples of it, right? So there has to be some there has to be some scaling factor, and another way of thinking of it is the energy that was in this single triangle now is spread up and down over multiple, an infinite number of frequencies. So that scale factor just represents the fact that some scaling has taken place because of the sampling. So in order to get this back to look like 1, is what we have right here, we have to build in a gain scale mathematically in the reconstruction filter. So that will be something that you will do, like I said, in most homework problems. You will track that through so you get the gain scaling to work out properly. So before we go on, I'm just going to show you a little demo, some demo apps that I have. I have these ideas embedded in the Jupyter Notebook for Chapter 4, which we'll be looking at eventually, but these are some things I created a long time ago because I wanted to have some animation. So the red waveform is an analog sinusoid, and I can vary the frequency of that sinusoid from 0 hertz all the way down, or all the way up to 1 hertz. And the sampling rate is fixed at 1 sample per second. So these blue stems are the samples of this analog waveform, and as I increase its frequency, we don't have as many samples per cycle of the red sinusoid, just because we're sampling at a fixed rate and increasing the frequency, so the number of samples per period is going to go down. And so I'm going to keep going. When I get to the halfway point, like about right here, where am I at? I'm just trying to get you to start thinking about samples per cycle and Nyquist sampling theorem. So each period of the sinusoid, which is fixed at, is at a fixed frequency right now, about 1/2 hertz. I'm sampling at 1 hertz, so I'm getting exactly 2 samples per period, right? That's what you should see, 2 samples per period. Now, I quoted the sampling theorem, and that'll be stated. I was about on that page, but I'm just sort of excited to want to show you this picture, I guess, or this animation. So this is like the minimum sampling rate. But people will say, and I will say mathematically, if you're being very precise with an ideal low-pass filter reconstruction, 2 samples is not good enough. You have to be slightly greater than 2 samples. And I'm going to show you why. I'm going to change the phase of the sinusoid. And if I change the phase of the sinusoid, the samples will not necessarily be taken at the peak, and in fact, they could occur like that. You find that, I mean, to me, it's really cool. It's like, that would be devastating, right? we'd get nothing. But the chance of the sampling clock and your waveform being synchronous is slim in a real system. But if that was the case, that's what would happen. You can see this demonstrated when you're working with the hardware in the DSP lab. But at any rate, if I increase this, then we start being okay again. So I'm going to put that back to 0. But now as I increase beyond the 1/2 point, I'm seeing less than 2 samples per cycle, and I'm starting, and this is now a visual perception thing, and all of your eyes might not work the same, but I'm just going to continue to increase the frequency of the sinusoid, and you can concentrate on the blue dots. It's like you're going for an eye test of some sort or another. You're seeing that the dots don't appear to be intimately related to the sinusoid in the same fashion as they were. And as I increase this, you're going to reach a point. You know that there's going to be aliasing, right? You just know that from, you learned it before. When am I going to start being able to see that those blue dots connect together to form the alias sinusoid? Well, it's already happening, but our eyes just can't quite see it. If I increase this a little bit higher so that the alias component is lower, I'm starting to see it now, but as I keep going up higher and higher, eventually there's going to come a time when you can see it, like right there. Are you maybe seeing it now? Definitely you can see it there, right? You know, the blue dots here are the alias signal from the sinusoid. You know what I'm talking about? Okay. It's really obvious there because it's just part of a cycle, but it's happening now as I back up again. Now you can probably see it better, right? Because your eyes are getting trained what to look for. You can see it running down through here. So I have a little switch on here. If I take this all the way back over here, I can have, if I turn aliasing on over here, it will make the red signal display the alias frequency. So as I go up higher in frequency and I reach the halfway point like here, now what's going to happen is it's going to show that the principal alias is going to appear instead. So now we're going to see I'm slowing back down again, lowering the frequency of the sinusoid because that's its alias frequency. See, now it's tracking. Whereas here, unaliased, aliased. Is it working? I mean, I'm just trying to bring some reality to this sampling theory stuff.
I'm wondering, you said we want our sampling rate to actually be a little bit over
2x, 2 times the highest frequency.
Yeah, a little bit over Nyquist. Does that create a periodic error where periodically we have a collapse of the tracking in the
I think you're thinking of the envelope of the signal. No, it won't.
No.
Because over time, you know, and that's the thing, we're only looking at a little bit of time. Over time, there will be enough information to reconstruct a signal from its samples. That's really what it comes down to, because in the frequency domain, what you should be saying from the notes over here is that I know as long as I can put a filter around that central spectral component, which is our fundamental or the original spectrum, and then throw away everything else, I should be good to go for reconstruction, right? I mean, it depends on if you believe the frequency domain or the time domain. I mean, I believe the time domain is what we live in, right? The frequency domain helps us explain what's happening, and if you believe that to be true, you should be able to run it really close, but the fact of the matter is, if it's right on twice the highest frequency for a sinusoid, it will be all zeros at some particular phase, and if you just say it's slowly drifting, yeah, the amplitude's going to come up and go back down again. But if you're reconstructing it with an analog filter, it would produce a sinusoid. It would be correct. I got introduced to this idea when I was teaching a short course when I was first a professor with another faculty member on DSP, and somebody in the audience said the sampling theorem doesn't work. I mean, there was an argument that occurred in the class. It's like, no, it doesn't work. So that kind of inspired me to create, this application over here. So there's another application too that I want to show you that we'll be coming back into later. Let's close that one. This one is looking at it in the frequency domain, and here I change the sampling rate, and B is the bandwidth. So the spectrum bandwidth, and I'm plotting the normalized frequency, so it's F over B. So 1 is always going to be the band edge. So now as I increase my sampling frequency, the alias spectral components spread apart, and we normally would think, and I have Python tools for doing this, so we'll see that later, that is going to be right at 2. That's kind of our minimum right there. Greater than twice the highest frequency, so we have to be a little bit greater than that, and if it's helpful to say that, so notice there's a little bit of gap in here, so a real filter can come along and be designed with a very narrow transition band. Okay? Now I'm going to do is, we'll come back to this later with the so-called bandpass sampling theorem, but now blue is our signal of interest. It's not a low-pass signal, it's what's called a bandpass signal, because it has this spectrum that turns on at some frequency greater than 0 and then shuts off at 1, its spectrum. And of course, it's a real signal, so it has a mirror image spectrum down here in the negative side. We're sampling at Nyquist, but now we notice that if I increase the sampling rate, we're still doing just fine. We know we can recover the blue signal. But now if I reduce the spectrum, this is the interesting thing that happens, and this is the bandpass sampling theorem in action. Lots of collision in there, and my cheap laptop doesn't have very fast graphics on it, so it doesn't have a graphics accelerator on it at all. But at any rate, it's fitting inside of there, and I have another narrower bandpass signal. And if I take this up to a very high frequency, like an RF signal that's on a carrier that's way up in frequency, then the spectrum of the desired signal gets even narrower. So now we can see how much over or undersampling we can get away with. It does have collisions. It has zones where they're called zones, Nyquist zones, where we can have clear, and then we can have aliasing, and then we can drop lower. We have another zone. So here, my ratio of the highest frequency, the sampling rate over the highest frequency is only 1/2 rather than 2. And this is called undersampling. Undersampling because we know the information of interest is in a narrower bandwidth, and this is what all the front-end processors do for software-defined radio. They do things like this. And here I can even, in this particular case, I can push it down even lower there. That's about the lowest I can go, and we'll have a formula here in a few more pages for the bandpass sampling theorem. That I would not choose because if my signal actually occupies this full band in here, there's no way I'm going to design a narrow bandpass filter that can perfectly extract it. I'd want to be in another zone further up here where I would be able to set it up so there's some overlap between them. Something like that. So if any of you work for radio people, and I know both of you do, this is the idea that would be used in most receivers, and we'll be talking about this in a more detailed example later, but this is the idea of undersampling and sometimes it's called subsampling, IF sampling. There's different names that kind of relate to the same idea, that if it's a radio signal, we can undersample it. And fundamentally, what happens here is that we're approaching a limit, but it's not an exact limit, depends upon the exact frequencies and the exact sampling rate, where what we're able to accomplish with this in the bandpass sampling theorem, we're approximately able to make the sampling rate twice the bandwidth of the signal, not the high-end frequency like it is for low-pass sampling. We have to be greater than that highest frequency, whereas in bandpass sampling we can get away with being approximately 2 times the width of the signal, or in other words, 2 times this width in here. And that's what, this is about 0.2, and that's what we were seeing way down over here. .4. So we're about twice the bandwidth of the signal. And I worked for a company called Navsys, and the president of that company, and I think she's actually still has her company up there off of Baptist Road, behind that big new warehouse that was put in off of along I-25, just to the west. I worked for her for a while many years ago, and she would argue with me that I only have to sample at greater than twice the bandwidth of the signal. And I said, okay, this is the limiting case of this guy right here, but if the signals are configured in such a fashion that that is what's going to result, that's not good. So the math that we have is actually more precise. It will say what zone you can be in where there's no collisions, and it might not always work out to be exactly half, because it might not mathematically be possible, but it's close to that. Is that acceptable, though? As engineers, it is acceptable, right? We know that discrete natures of things and things like that, it will be approximately so. I mean, that's why you took calculus, because you learned about in the limit, right? And I don't know about you, but when I was first taking calculus, I was bothered by in the limit, because I had never seen calculus until I was at the university. So things happen differently in the limit than they do before you get to the limit. So kind of cool. I'll probably come back and refer to this again later, but we'll be seeing this. This is big, really big, in terms of people that work in RF systems with DSP. And I'm in the midst of that right now, and that's the motivation behind multi-rate sampling, too. So there's some examples. This is just a single sinusoid. This is just looking at, we have to sample at greater than twice omega naught, and if we are greater than 2 times omega naught, the first set of translates, which are really sitting right in here, are just not going to be bumping down into this band. And then we can reconstruct with a filter. So here's the statement of the Nyquist sampling theorem. This is certainly, this is the low pass case. And so the terminology is the rate is twice the highest frequency, and it says be greater than twice the highest frequency. So now we have a bit of business to take care of, and that is we've so far been talking about the spectrum of the analog signal, and we've used the spectrum of the sampling signal, X of S. We haven't done anything about getting it into our system. So what we want to be able to do is say, we have, let me get this to delete. We want to tie the discrete time signal spectrum, the DTFT of the sequence X of n, to the spectrum of the analog continuous time waveform X sub C of t, and that will be relating these two together. So the way we do that is we start backing up from our Fourier transform theory in the continuous time domain and just say if we have the spectrum, if we want to get the spectrum of our sampled waveform, x sub s of j omega, we would just take the samples and we would use the discrete time Fourier transform of those sampled values will give us the spectrum, the same as the Fourier transform in the continuous time domain, because we're talking about making use of this Fourier transform pair. So once we do that, and this is like a hand-waving thing. I mean, the math here is concrete. It's just, you can see that I'm going to go through a little equality thing. I'm going to say, so what I see right here is for the analog signal samples and using a Fourier transform pair from the continuous time domain, and then we drop down here to say, what if we had just the sample values x of n and wanted to do the DTFT of that, where instead of using omega in there, little omega, I let omega be equal to capital Omega times t, the sample spacing. Well, then it looks like this x of e to the j omega t is really the Fourier transform of the sequence x of e to the j omega. So they're related intimately. They're the same thing, just with a change of variables. So this relationship here is going to be our very existence for everything with sampling involved. If you want to go from the analog domain back out to the digital domain, it'll always be connected through this mapping. And then it will take into account the fact that we have frequency translates when we sample. So those frequency translates in this blue boxed equation are frequency translates of the original analog signal spectrum now showing up as x of e to the j omega. And this doesn't break any rules because this just says that this superposition of all of these frequency translates of the analog signal end up filling up the entire frequency axis in the discrete time domain, and it's periodic with period 2 pi, just like we had back in chapter 2. So it's all like, if we're on either side, we're shaking hands saying, yep, we're consistent, and it all plays together. Without sampling theory, everything is just as it is, but with sampling theory, we're allowed to connect the continuous and discrete time together, and it's this little equation that tells about how the axes match. So it's at this time that I like to show this picture, which I showed to somebody earlier, maybe it was last week or the week before. So in the beginning, we had when we were talking about the DTFT, we had things going on 0, pi, 2 pi, and then repeating. In the omega domain, capital omega domain, and the frequency axis, we have these corresponding points. Pi corresponds to half the sampling rate in radians per second, divided as radians per second. And then 2 pi corresponds to omega sub s. And then if we want to put it in hertz, how did I delete that? I don't even know how I did that, but it's gone, so it's brought again. I think I hit the button on the side of this, which I don't really know for sure what it does. So in hertz, which is the way I like to think with DSP systems between analog and digital, 2 pi corresponds to Fs and pi corresponds to Fs over 2. And, you know, all of that is happening because that's true. And if I just throw all this stuff together, I can do any combinations of things I want. I can solve for omega from little omega over t. I can notice that capital T is 1 over Fs, so I can just move things around kind of at will. So I'm using the various substitutions to get all these labels on the axis, but fundamentally it comes from little omega equals big omega times t. But if I want to throw out the pi just put in Fs over, put in 1 over, or t equals 1 over Fs, and I can have this relationship, or if I want to do it differently, I can just move stuff back in again. And I'll kind of be using that all the way along, but I want you to be aware of that. And I guess in terms of working any sampling theory problem, it's kind of like being spatially aware of something. You know, you're in an unfamiliar environment and you're moving around, looking at things. What's your spatial awareness? It's this little omega is capital omega times t, or in terms of sampling frequency in hertz. So just be aware of your surroundings, and it'll work. It's not complicated math or anything. And I'll just keep going at it, and I'll keep reminding you of that relationship. And if it helps to draw pictures, and for me it almost always does, and I think I've told you this, even though I have a wonderful iPad, the large screen, I can draw on it to scribble, but sometimes when I want to do something, I just have a little pad of paper and I just scribble things down. I do this all the time when I'm trying to think something through. I need to write some math literally on a piece of paper, and then eventually maybe I'll move that into my Jupyter notebook or something like that. That's probably because of my age or something. I'm paper and pencil more. I just feel more relaxed. Apple Pencil is pretty good, but I like the paper because I can just throw it away rather than have to erase the screen or something. So let's look a little bit now at reconstruction. What's the actual details of reconstruction? And we'll see how that works here. So this again will just focus on an analog waveform in terms of its samples, and if we're going through, in which we're developing the discrete to continuous converter, we'll just be saying that at some point at the end of our DSP system, before we go back to the analog domain, we'll take the samples and we will put them back on the time axis with some device. It'll be called the D to A converter, but from a mathematical standpoint, we'll say for understanding how reconstruction works, we're going to assume it's going to be placing delta functions on the time axis. In reality, we know the D to A converter generally does it with a zero-order hold. So it puts the sample out on the analog side, it holds it until the next sample, and then it drops to the new sample value and so on. But just to make the math more understandable, let's just suppose it's putting only a delta function out there in the continuous time axis. So the reconstruction filter will have some frequency response and corresponding impulse response. So if we look at doing the convolution of this x of s of t with the impulse train with the delta function in it and the impulse response of our filter, we see this relationship right here, we're taking samples and making them set the amplitude of the impulse response, and as the sample value changes, the impulse response shifts up and down the time axes. Now, going back to the theorem, or one of the transform pair table results, for an ideal low-pass filter, it's a brick wall, and we would use this capital pi function that I defined, and if you need to look at that some more, you'll have to go back in the notes, but I'm putting the frequency variable on top, and the notation of the capital pi function is on the bottom inside the argument there. That is the full width of the pulse. So this is saying that in the frequency domain, I've got, I shouldn't say pulse, I should say spectrum. So the full width is 2 omega c, so that's why that sits in the denominator, because the definition of that rectangle function just says from the center to one edge is half of that denominator, and going off to the left it's half, so it's plus and minus omega c. And that becomes, when you inverse Fourier transform, a sinc function. So that says that our impulse response to the ideal low-pass filter is a sinc function, and the rate at which it's rippling involves omega c over pi. Put that into the full reconstruction filter, and this would be the ideal theoretical reconstruction of a signal from its sample values x of n. And the sinc function is the impulse response to the ideal low-pass filter, and it serves the purpose of interpolating. And everybody learned about interpolating ages ago, right? I can remember that in high school math or somewhere. I don't know. Can anybody remember where did you first learn about interpolation? Anybody remember? I can't remember exactly. So if you organize that a little bit further, you can get it into sine x over x, and then you actually have a reconstructed waveform model, a little bit more visual, and this becomes the operation of the discrete to continuous conversion that the book refers to. It's always going to be a signal that comes along and gets converted back to an impulse train. This is just the conceptual view in mathematics at a sample period of capital T, and then there's an ideal reconstruction filter that is set by the bandwidth in hertz being 1 over T, and that will look like then if we have an analog signal, we sample it, and this is just again the concept of how you go from analog domain samples and then reconstruct it using the ideal sinc function. I think James, he just walked out. Unfortunately, I was going to make a point. Oh well, I'm going to keep going. How do the waveforms get put back together again? And he was talking about, when I was showing you that animation, is there a collapse in the envelope? And as long as we have time running on for essentially infinity, you know, infinity in the sense that we look at any small interval, we will have impulses that occurred before and after our little focus zone, and those impulses will produce tails. So this impulse function this impulse produces this sinc function, and notice that it has a negative time axis tail that ripples around, and it's contributing to the waveform all the way along, both before and after that signal. This is a non-causal filtering model, but it's still the idea that we can interpolate. In a real system, it's going to be a finite impulse response, but it still interpolates. It'll just have some delay. This is like the no delay system, which is not possible because we can't do a non-causal operation. But what this picture is supposed to be showing you is that the sync functions combine and that reconstructs the signal. Does that make sense? I didn't create an animation for this, but I have done it in Python before, or perhaps in Julia, I don't remember. So what we've been describing is the ideal discrete to continuous, and the reconstructed signal will be the original input signal spectrum through the eyes of the reconstruction filter, and the reconstruction filter is always going to produce just in the band that it operates in. So plus and minus, the bandwidth of the filter will be a low-pass filter, and it will run from minus Fs over 2 up to plus Fs over 2. Probably didn't quite get that right in here when I was talking about that, but the filter is actually, if we pick the ideal value, omega c will be equal to omega s over 2, or the cutoff frequency in hertz will be Fs over 2, because that's right where we go from one Nyquist zone to the next, where the alias, we have to stop the aliasing, and that's what this does. So in the end, this is the matching system, the discrete to continuous converter. And I was looking for where it occurred in here. There's a gain scale factor of capital T inside of here, though. So that is inherent in the reconstruction filter. Remember, there's the 1 over T when you sample, and then you put it back together again to get the gain to match. They build this gain of T into the discrete to continuous converter, and it's kind of subtle, but it's inside this filter. So that filter has a gain of T. There it is right there. My eyes did not see that. It's right there, though. And that makes the peak be 1 in the impulse response. And James, you just walked back in. I was doing this little discussion here when I show the reconstruction, when you were asking me about the envelope and stuff. This shows you how ideally, at least, the interpolation function placed at each sample produces this sync function, and as they all combine, they produce the waveform again. Was that on your mind?
Oh yeah, I believe it. I figured there had to be something that would regulate it or pull it towards the right frequency.
Well, pull it towards the right amplitude, though. Reconstruct the waveform.
Yeah, we're talking about an amplitude envelope.
Yeah. You use digital oscilloscopes a lot, you know, the DSP-based oscilloscopes in the lab. When they first came out, people were not believing them. I mean, I lived through that generational change, and with Keysight being Agilent and then Hewlett-Packard before that, as those scopes came out, they wanted us to have them as soon as possible. So they started donating equipment to our lab, because the reason why why our department is here is in large part because of them. Does everybody know that history of our department? It has to do with Hewlett-Packard putting a division here and then wanting to make sure there was an electrical engineering program that they could interact with. So they've always given us equipment or given us equipment at a steep discount and so on and so forth. But when the digital scopes came around, there was this random periodic sampling is what they were doing in the very beginning. So they would randomly sample across a waveform, and then they would take those samples, like in this picture right here. Suppose they were not quite periodic, but they were randomly sampled, but it was a periodic waveform, so they knew, like for a sinusoid, they could fill in all the values between where the samples were using some interpolating function inside the scope. And the purpose of that interpolator function inside the scope was to make us people that were used to the analog scope be comfortable with it. It looked like a real analog waveform, but they were putting it together literally using this type of idea right here, some secret function. And I worked for them on a FFT project where they were going to add FFT functionality to their scope so they could do a spectrum, and they eventually did all that. The subject came up about the interpolating filter, and since I was under an NDA when I worked on the project, I got to see what that was. It was kind of like it's something that they had protected and they didn't want to reveal it, but every scope maker has to do something like that. They have to have some realizable impulse response that they can take the samples and to display. It's just for the purposes of the display, though. Does that sound believable? Because we're used to modeling things like sinusoids or square waves, triangle, and so on. We want to see the dots connected with lots of resolution, so that's what they had to do back in the early days when they had random repetitive sampling. And now they do things similar to that, but they sample at much higher sampling rates than what they did in the beginning. That was related to technology as well. They couldn't sample as fast. Now, what do our scopes sample at? 10 gigasamples, 20 gigasamples per second. And how does that work even? That's a trick. That's trickery too. They don't have one A to D sampling at that rate. They have A to Ds of lowering sampling rates that are staged in time that can take samples and they can sort of bang them off, bang, 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 and then they get more samples effectively from multiple converters. That's all been stuff here, but nobody here has worked in that group, right, as an intern. The instrument makers are limited by technology just like the product developers are. We all have to work with the same kind of suite of technology and be creative to try to make test and measurement be useful for the designer. Okay, so now the focus will be on, for a little bit here, on processing discrete time or continuous time signals with discrete time processing. So this is something I'll refer to a lot over time, rest of the semester actually. This is the so-called C to D, H of E to the J omega, D to C system, or A to D, H of Z, as in the Z domain rather than the frequency domain, D to A system. The bottom line is the system that can bring in an analog waveform, do some processing on it, and send it back out as an analog waveform. But as I was pointing out earlier at the start of today's lecture, we could divide this down the middle, and we could have a discrete time system like an audio playback system, just have the back end for listening to audio music or being a receiver, a radio receiver. And if we're building the front end of our system, we could have just this part of it where we are connected to an antenna or connected just to an audio analog system, microphone, whatever, keyboards, anything that will bring a source in, and then we can digitize it and store it or do something with it. We don't always have to visualize this as a play-through or loop-through system, but in the DSP lab, this is exactly what we implement. We have the loop-through system where we get to build to our liking what we want to have inside of here. So what does that look like mathematically, just to trace it through and understand the limitations on it? We have our signal, which is obtained by sampling the continuous time waveform, and we now have this relationship to say what is the spectrum of the discrete time signal in terms of the analog signal spectrum. It's this superposition of translates of the analog signal, and of course if it's not band limited we're going to have aliasing, but we'll cope with that accordingly. We'll put an anti-aliasing filter out in front, but I'm not quite to the point of talking about that. And then we go through our system, so the x of n that's inside of here will become y of n at the other side of the DSP system, and then we'll be able to reconstruct that using our ideal reconstruction model, and we'll be able to say that the reconstructed signal looks like a filtered version of the discrete time signals spectrum. So what is that going to be? Well, we have to know what the relationship between x of n and y of n is, and then we can finally relate the input signal to the output signal. So we know that y of e to the j omega is h of e to the j omega times the input sequence spectrum, and then we can stack it all up together and have pretty much this form right here, where this is the input signal spectrum. But if we make some assumption that the input signal spectrum is band limited, it's 0 for frequencies greater than the Nyquist frequency, which is pi over t, then the output spectrum will just be the input signal spectrum, x of c, times whatever the frequency response is of the system. And that's really what we'd like to be able to say. We built a software-defined analog waveform processor. Does that sound great? I mean, I'm sorry if you wanted an analog domain processor, but that's not what digital signal processing is all about. We're all about making things in the discrete time domain, making programmable devices to process waveforms. So with that condition true, and the way this is made true, so this whole idea right here, how is the signal band limited? We make it so, if it's not truly band limited. And you might say, my speech waveform is only going to go up to, I don't do a really good job of squealing at ultrasound with my vocal cords, but it's going to go up to maybe 20 kilohertz at the most. I know I can't do that high, but at any rate, so we band limit it, and we have to band limit it because if our front end doesn't have some band limiting action in it, it will accept either noise or interference and other things. And now, from the sampling theory that we've already looked at, all of those spectral components will alias down and they'll be undesirable, like bat chirps or something would be audible. And that's exactly what I did years ago at the Bat Cave at the Cheyenne Mountain Zoo with some students in a senior design project. Hewlett-Packard then had donated an oscilloscope and some other equipment, and then we developed some electronics with the students that would frequency translate the bat signals down to audible frequencies. So I haven't played that for you, have I? It's somewhere. It used to be on my old website, so I can't just go pull it out. It's stored on the web server. On the old server, I could pull it in, but bats were eating a piece of cantaloupe hanging from the ceiling in the bat cave, and these were fruit bats. Fruit bats love fruit, and they just were flying at it like crazy and chirping or echolocating, and it's pretty cool. It's not at their echolocation frequency, but it's translated so it could be audible. And I captured an isolated bat flying across the cave, and that's the one that I like the best because you hear it chirping multiple times. It's doing a radar type operation. It's like it sends out a blast and then it it sends out another one, and it's got a decay to it. So it's, I think, a good model of how our radar systems work, how bats can echolocate. They're seeing the wall over there, they're not going to hit it. They're sending out their chirp, and the chirp lets them know in their brain how to avoid a collision. If you don't like bats, has anybody ever been to a zoo where the bats are free? There's certain bats around the country I've been to where they're flying around, or you look up in the corner and there they are up there, and it's a little bit creepy, but they're not after us unless they're, vampires are the ones that will eat human flesh. I don't really worry about it too much, but pardon me?
They eat blood. I worked at a zoo where we had vampire bats.
Okay.
And we used to have to go pick up jugs of food for them from the slaughterhouse. We would have an anti-coagulant in it.
Okay.
Yeah, anyway.
Did you have to wear a suit when you went in the bat?
I did not go in there because if I wanted to be a part of that crew, I had to go get a rabies vaccine.
Okay. I can believe that.
Those are miserable.
Yeah. Well, we had to go in the bat cave and put our ultrasound microphone array in multiple locations. It was a fun project. I really enjoyed it, and the students got on TV because the TV station came in and did some videoing. They took it down. I don't think they have it anymore, but it wasn't really all that exciting unless they were getting fed, because you didn't hear a chirp. They don't chirp that much when they're just hanging. When they're hanging, they're not doing anything, but when they're flying, then they are chirping. So I actually studied a little bit on the biology of bats at that time too. So let's take one little example, and then we'll probably go for the break. So this is an interesting observation at the end. Fundamentally, it starts out as, suppose we have a ideal digital low-pass filter that cuts off at little omega C. We're now going to put that inside of our C to D, H of E to the J omega, D to C system. So continuous to discrete, H of E to the J omega filter, and then discrete to continuous. So the effective model of this filter, when we take into account our transformation equation, it's omega C over T, and how did I get that? I'm just doing this to remind you that we have this fundamental equation. Right, or I wrote it before as, so just come back to that equation and say, I had an original analog discrete frequency of omega C, and the first version of the equation written right here just said to get it in the big omega domain, I have to take little omega and divide it by T. So it's omega C over T, and that'll do it. So that's what that radians per second looks like, and always do what I guess my chemistry teacher in freshman chemistry taught me, always balance units, right? So when you look at this, if you're having a brain fade or something, capital omega is radians per second, little omega is always radians per sample, and so we have radians per sample divided by sampling period. So fundamentally, though, radians per sample just has units of radians. The per sample is just convention to say that that's what it is, but you're dividing by seconds. So you have radians over seconds. Is that helpful? Have any of you not ever been saved by being able to do something like that on the fly? I mean, when you write something down, check your units, and if they don't make sense, that can definitely save your bottom. You might catch something at the last moment. It's like, wait a minute, the units don't match. What did I screw up? That's what I always think of. So there's the cutoff frequency, and now when we put our picture together of the analog signal coming in, it getting sampled, there's all its replications up and down the frequency axis, or frequency translates, like I showed you in the animation earlier. And then I'm putting the other frequency axis on here, so big omega, converting it to little omega, so this is our little omega n, and now our digital filter cuts off at omega c, so we're band limiting the signal if we make omega c less than a little omega n, and there we've got a spectrum that looks like a house as opposed to a triangle. If you want to look at it that way, it looks like the profile of a house. So what is also cool about this is if we view the cutoff frequency as being a variable, then we can move it around. So we can move it in and out on the frequency axes, and we can use it to prevent aliasing. So we can relax our aliasing conditions. So suppose there was some other component that was leaking in, like there was a sinusoidal tone. It will get in through our sampling system because we're not protecting against it because we don't have an anti-aliasing filter, but in the digital domain we can make sure that tone gets blocked because our digital filter on the inside will reject it. It won't pass through. That's what my comment is there. So we're going to look at some other examples, but I'm wanting to take the break right now. We're getting ourselves queued up for our power shutdown. I'll talk about that I talked about it before class started, in the video earlier, so I'm not going to put it on the recording again. But let's take the break. Get this to pause. Recording. This is another example of how we could visualize just tracing some waveforms through with sampling theory and aliasing. So here I've plotted parts of the spectrum of some digital filter that's in a system, and I've got my three axes up here. You can see that I'm kind of a fan of that. Here in this particular case, this little f is actually hertz. I said early in class that I wouldn't be consistent, and I'm not. I actually don't like using big F. I just like using F in hertz and not F in normalized frequency. I generally don't use F as analog F over Fs. I just use omega and big omega. So this is in hertz. So in this particular problem, we got the magnitude and phase response for our digital filter, and here is that we're going to sit this filter between our continuous to discrete and discrete to continuous and look at what comes out the other side. So we're going to do a sample spacing, capital T, of 0.2 seconds. So the sampling rate is 5 samples per second, and we're going to put in 3 sinusoids. One is at 1 hertz, one is at 6 hertz, one is at 4 hertz. So we should stop right there. What rule are we breaking? Because this breaks some sampling theory rules. If we're sampling at 5 samples per second, what's the highest frequency we can take at the input without aliasing? 2.5, right? So the 1 hertz is the only one that's going to come through faithfully. The signal that's at 6 hertz is going to get aliased, so it's going to fold down to what frequency? 1 hertz, right? Or no, 2.5. It's sitting up there at 6 and it's 5. Yeah, it's 1 hertz. And then the 4 hertz is going to come down at 1 as well. This problem came from another book years ago, but the point of this example was all three of those signals come out at 1 hertz, but they come from different locations just because of aliasing. But the idea is to track it through too. So here is the time domain picture of what the waveforms look like going in. So I'm showing just, I guess I'm showing only 2 of them. I'm showing the X1, which is at 1 hertz, and then the X2, which is at 6 hertz, coming in. And remember, you guys that came in late missed my demo app that showed things, aliasing and moving with sliders around. But at any rate, because we saw that already, we can see that the samples of the 6 hertz and the 1 hertz are going to be the same. They're going to land on top of each other, and we're just going to lose track of the fact that we have all those cycles in between because we're not sampling fast enough. So in the end, what happens is when they all go through the A to D, D to A system, we have the 1 hertz sinusoid comes in. It is in the pass band of the filter, so we just go back up this picture and say, what is the amplitude attenuation? So the 1 hertz signal effectively on this axis is 0.4 pi. And if you need to track that out, what would we have to do to make sure we understand that? We have 1 hertz sitting right in here, and we go back to our equation. That's how I would like to write it out, but you can carry it through more gyrations in the beginning if that's more beneficial to you. But once you understand the relationships, you can, this is how I think of it as normalized little omega frequency is in radians, but it's really just F over Fs, the normalized frequency, times 2 pi. So 2 pi always keeps plopping in there to get us in those radians units. But so this would be pi times 1 over Fs was 5. So it's going to be 2/5, which is where the 0.4 comes in. Make sense? This is not hard calculus or anything. It's just doing simple math, that it's coming back to these same transformations. And like I was calling it earlier, it reminds me of my wife. I have twin sons, and one son is my wife. When he was younger, he was always bumping in and crashing into things. He was kind of not paying attention. She would always say, beware of your surroundings, beware of your surroundings. So that's why I was thinking of that earlier. It's like, what are our surroundings? Our surroundings are we have these relationships. We know how to go from one axis to the other, so we're totally aware of where things sit. The collision part doesn't really make sense, but still being aware of your surroundings. So we're at 1 hertz corresponds to 0.4 pi. So on our digital frequency, our digital filter, it has some amplitude A at that location, and it will have some phase down here. Whereas we go into our 6 hertz signal, which was at F2, it's sitting right in here. 6, and so it picks up the exact same value of A, and it picks up the same phase. And then our 3rd signal, which was at 4 hertz, it picks up the same magnitude, A, but it picks up the opposite phase. This goes way back to when we were talking about sinusoids and things that lead to the same samples or the inverse of the samples because of sine being an odd function and cosine being an even function. Remember that discussion? It's hard to explain that stuff in the beginning, but once you start seeing it in action here, now you say, oh, I get it. unfortunately, it always seems hard to get into something, and I think that's probably because in the beginning, when we don't know certain things, we just don't have any connection, like, why do I care and what does this mean? But don't you find that as you move into something more and more, it's like it's all starting to sort of get locked in your brain. It makes sense. I connect those dots together just fine. In other words, here it's the case I was using the sign, so that's what made that happen. At any rate, that's what we get out of here. We get all the same frequency, and we get a phase and inversion on the 4 Hertz signal. So this could be an exam question, but it's not super exciting. This had too much setup to it, too many pictures to draw, things like that. But does anybody have questions on what was going on there? I'm going to jump to the Jupyter Notebook. I have this in there too, so we can see it over there. This chapter, which I just reposted last night because I had some things that weren't totally good by me, I reposted both the notebook and the PDF rendering of the notebook that you can see on the website. So I maybe come back up and look at some of these things with the sampling theory, but right now this is this problem. Right? So this should be example, whatever it was in the notes, except that I modified it slightly. I said 1 kilohertz, 18, and 22 kilohertz. It's the same exact idea, it's just different frequencies and different sampling rates. So I set the sampling rate at 20 kilohertz, and I have this little function I wrote for signals and systems for dummies called principal alias, and all the principal alias function does, I just look at it and I'll do Shift Tab. It'll calculate what, when I used to teach 2610, was called the principal alias value. That was what that book's notation was. And you put in what your input frequency is, you put in your sampling rate, and this calculates what that alias is down to, like 6 hertz, alias down to 1 hertz, 4, alias down to 1. You can pick any value along the frequency axis, and it will be like an accordion. They will all alias down to their principal alias. In this equation up above there, it's the absolute value of the rounding of the numbers that does that. And if you just put in a sweep of frequencies for Fn, for a fixed Fs, this is just for like the CD sampling rate developed for the compact disc, sweeping from 0 up to 100 kilohertz. So anything above the folding frequency of 22 kilohertz begins to alias. So, you know, if you draw a horizontal line on here, these are all the points that will come down to the principal alias. Am I starting to make sense on that? It's what you would hear as opposed to after it's been sampled. These are alias down. So I use that principal alias function in here as a check, and I just said 2, 18, 22, plug in 20, and I'm going to get 2 for all of them. And if you don't have the principal alias function available, what you have to think about then is you have these zones there. If you're sampling at 44.1, you have a zone. So the first zone goes from 0 to Fs over 2. So that's all the principal band. And then the next zone runs from Fs over 2 up to 3 Fs over 2, which is up here, right up here. So then you're taking what the frequencies are relative to the sampling frequency in this next pair of zones. And then the next pair is at 2 times Fs over 2. And it's the same idea. You know, the book doesn't really, and I'm not making a super clear understanding in the notes, but if you look at the spectral plots, you can see this idea of the zones is just where the bands are related to Fs over 2 and all its multiples, and how the spectral translates jump from around 0 up to Fs, and then 2Fs and so on. So it's how those would alias down. So here I ran that simulation, and here I'm using the cosine. It looks like I'm having problems with my notebook. You can see the kernel is busy. Why is it busy? I don't know. The computer doesn't like running a video recorder. It should eventually get finished, but I don't know why it's taking, so there it is. So I use I use cosine. So if I was to go just replace these, let's say with sine, this is a new feature of the new Jupyter, I guess. Busy, trying to execute 0 of 1 cell, running at 20 seconds. It's kind of cool. Pardon me?
I've been waiting for that to be on the web version. That's why I use the VS Code version, because I can see how long
Oh. Yeah, I think VS Code is slower, though, per execute cell. I use them both. I mean, this past week I was debugging, and I had to go to VS Code to debug inside a Python class. So now we're seeing the one in the middle is inverted. So back over here to the notes. The next little example here is impulse invariant design, and this is a topic that really refers to a type of digital filter design, and I think I've probably given you the homework problem that relates to this. There's a homework problem that's very, very similar to this example and just kind of does almost the exact same things as this. But what it says is, suppose we want to implement in the discrete time domain a digital filter that emulates this continuous time system that would have some analog impulse response, HC, little hc, and big HC of j omega. So how do we do that? How do we get that design? So one type of digital filter design technique is to say, and this is historical with the fact that analog filters existed long before digital filters did. So people said, we'd like to have a Butterworth, we'd like to have a Chebyshev, we'd like to have an elliptical in the digital domain. So they developed filter theory ideas. And the two main techniques, and we'll probably talk more about this later, there's a whole chapter on this that I don't cover, but it's chapter 7 or 8 or something like that from way back when I used to teach that. There were two main techniques, impulse invariant and bilinear transformation. If you take the lab, which James is taking, he's the only person left in the class that's taking it, there is a discussion, more discussion on the bilinear transformation. If you were to look in one of the labs, which are all available on the website, you could see where I go through that. But you could also see it in the notes way up in the upper chapter. But at any rate, the idea was this. Let's just take our continuous time impulse response, sample it, and then this looks kind of very convoluted, but it says take the analog signals frequency response, or the filter frequency response, inverse Fourier transform it, and then replace t by nt. That all makes sense, right? If you can do those transforms and operations, then we have our discrete time impulse response. So then we can say, oh, the spectrum or the frequency response of that impulse response sampled from the analog domain's impulse response is just going to be this. And it's all the spectral translates of that frequency response. So The only thing that has to be done is because in the sampling theory representation, we have this 1 over t. So again, just like when we were talking about our D to C block, we have to put a capital T back in to get the amplitude scaled correctly. So a design in MATLAB or Python might be like this. This is our first order analog low-pass filter, or RC low-pass filter, time domain, S domain, and generally if you're doing the impulse invariant design technique, you actually work in the S domain, and then you use an inverse Laplace transform. The inverse Laplace transform here is this 1 over RC e to the minus t over RC, and if you were doing it in a real design, you would, like I said, you would do an inverse Laplace transform. And people that would be doing digital controls might think that they would like an impulse invariant design. That's what I've been told, that people in controls really are used to analog controls in the beginning, and if they want to do a digital controller, they might decide to just mimic an analog controller very precisely by having the impulse response match perfectly. And they can do that because they can sample at a very high sampling rate, because I'm going to show you over the bandwidth of the system. I'm going to show you what this does, though. So I'm going to go to the Z domain for my digital filters impulse response. So I'm going to take this H of n, which is this. And remember, I talked about this one day. So RC, you can see, is 1 over 2 pi times F3, the 3 dB frequency of the RC low-pass filter. So the 3 dB frequency of our RC low-pass filter in the Z domain is this. First order. I said I would get to this, and here it is. I mean, weeks ago I said we'd see an RC low-pass filter showing up as a digital filter equivalent. And originally I did this in MATLAB, but Python, same idea. So now I'm going to go ahead and put in a gain scaling term, G I called it here, rather than just T. So it's G to make the filter gain be unity at DC. And there's the factor. So it's not quite T, it's this is what makes the gain unity at DC for a digital low-pass filter. And here's the code that I wrote. It's written in Python. I didn't say that up above, but I wrote this out in Python. And I just went ahead and the software is messing up. I think there's more than one plot in here. But I just did some frequency response plots, and this is definitely not right. I was having problems with this tool not rendering everything on my PDF at breakfast this morning. So I can go back over to here. Pretty sure I have this example in here. If I didn't put it in here, we'll go do something else. That's definitely not it. I think I probably thought the notes were good enough. So I can do this, though. I can get my notes up immediately if I make this work. There it is. See, I knew there was more there. Be wary of a PDF viewer. Sometimes it doesn't work properly. Has anybody else ever had that problem? Okay. It's just so they can happen. I have Adobe too, I have everything. But, okay, so the idea that with this picture is that suppose I'm trying to model a cutoff frequency at 0.1 hertz and I'm sampling at 10 hertz. So I'm at 1/100th of my sampling rate. So the orange is the digital filter, and the blue is the analog RC low-pass filter. So you can see down to better than 20 dB of stop band attenuation. The two filters match pretty good, but at the folding frequency, it's already coming back up. And, you know, there's a difference between the two filters. I mean, by the time I get to the sampling rate, I'm back to where I started from. I don't really have a filter anymore. And if I suppose I try to set my cutoff frequency at 1 kilohertz, I meant to say kilohertz rather than hertz, and I'm sampling at 10 kilohertz, it's even worse. And if I was to go all the way up to cutoff frequency of 5 kilohertz, which is my folding frequency, I essentially, in my Nyquist band out to here, I have very little filtering action at all. That's kind of the bottom line. It's what's happening up above here is like, I don't really care about that. I'm in the discrete time domain, so my useful band of frequencies is 0 to fs/2. But it's kind of, I remember I had a graduate student working on something, and he was doing a simulation, and he said, this is my filter, and I'm going to band limit the signal. And I was saying, wait a minute, you're like this last case here. Your filter is really not doing anything. Think about what you're doing. If I was designing a higher order impulse invariant design, it would be more faithful, because I would have less aliasing. But because I have aliasing, because the frequency response doesn't roll off fast enough, the impulse invariant design suffers. So we have other techniques that we can get away with, or we can use, and really a higher order filter is the biggest solution. But in a control system scenario, they might use a sampling rate that's maybe even 100 kilohertz, and the control system's time constant bandwidths are very low. They can oversample it a lot. In DSP, like we're using for RF and audio stuff, we don't generally have that luxury. So we might have to do some other technique there. Oops, didn't want to do that. I wanted to go back to that guy. How do I solve this problem? This morning, when it didn't show something further up, I started it and stopped and restarted it, and it reappeared. But see, now it still got frustrated and didn't render everything. Okay, so there's a little interesting example in here that's in the book called Continuous Processing of Discrete Time Signals. I put it in my notes because I was using that as an example, and now I sort of regret having done this, but I get value out of this, which I'm going to show you in the Jupyter Notebook. This is like, who would ever want to do this? If you're a DSP advocate, why would you want to take a digital signal, take it back out to the analog domain so you could do some analog processing, and then take it back in again? Does anybody see why? I mean, it's novel, but it doesn't seem like it's really what a DSP advocate would say. I mean, you have to understand that what I'm working in my work is doing DSP implementations of all kinds of things, but we're looking at things, applying it into systems that were fielded back in 1980. So in 1980, when the TDRSS satellites network was put up by NASA for Space Shuttle and other things, they were just bringing digital into most of the hardware. So there's a lot of analog processing techniques that are utilized. So they might have thought about something like this way back then. But it makes me think that was an example of how to get a non-integer delay, but now that we're in the DSP domain, we can get a non-integer delay by other means. And what we're talking about is the ability here to say have a frequency response, which is e to the j omega delta where delta is not necessarily an integer. And that could be very useful in aligning edges of waveforms in the discrete time domain. So one way of thinking of that is the sync function can be used as an interpolator in the analog domain, but we're still limited to one sample delays. But if suppose we wanted to approximate that, we could get a half sample delay very readily just with a FIR filter. And that's an example that I have in here where I'm just going to use a moving average filter. Here's the impulse response of that filter. It's just 5 ones, and what it implements then is a nice half sample delay. But to take that even further, this will be the last example in Python, but I want to just show you some tools that are available. Oops, I didn't want to do that. I wanted to get into here. So bandpass sampling theorem, which I haven't looked at yet. So here is the 1/2 sample delay. But in the digital communications module, digital comm, I have a function called time delay. And this uses a Lagrange interpolator. It's a third order interpolator. And here's where it has an inherent delay in going through the system, but once you get it up, you can delay in very fine precision, whatever you're after. It has a bandwidth limitation, but you can see after the transient passes by, these two waveforms are getting fractional delays that are wonderful. And then that function also has an option. Time delay has a function in it. And it's using an efficient Faro structure. It has built into it the ability to make this delay in samples, which can be any float number. It can actually be a function of time itself. So that's useful for either audio effects like something that was developed a long time ago before we had the capability for rock music. It was called flanging. Has anybody ever heard of flanging? Do you know why it's called flanging? It was where they had two tape recorders that they wanted to create like a wowing or warping of the time axis. So as the tape reels were spinning on the recording process, you could put your hand on the flange of the tape recorder and warp the time axes. So it's called flanging. And it's used in a lot of rock music back from the 70s and 80s, and now can be done in DSP. So it's actually talked about in the DSP lab, but I got asked to explore this when I worked at RT Logic, and there's a time varying delay element, and it was talked about in a research paper. So this is just showing you here that I made the time delay increase linearly from 1 to 5 samples over just a few samples. So you can see it's stretching it or compressing it. And it can be used for audio to introduce a flanging effect. It could be used in satellite communications if you wanted to take into the account that you're talking to a satellite that's on a non-geo orbit, so it's actually coming and going from you, or modeling in with Doppler and such. So our next big topic, and we will switch over to reviewing for the exam, will be changing sampling rates by a rational number. So we're going to start off saying we have x of n, which are samples of the analog waveform at spacing cap t. We're going to want to change it to t prime. And t and t prime are not equal. Typically, t over t prime is rational, but guess what? In the toolbox of functions I have in Python, I also have a Faro resampler, so you can come in and arbitrarily change the sampling rate. I built it originally because I was working in synchronization algorithms for digital comm, and I wanted to distort the time axes to make it look like it was sampled faster or slower, as if to say the transmitter over here has a crystal clock, my receiver has another crystal clock, but the crystals have a ppm, parts per million, difference. So when the signal arrives at me, it's sort of slowly walking one way or the other, depending upon the difference between those two oscillators. So a Faro resample can model that. I use that in the work I'm doing right now to represent asynchronous processes. It's not probably hitting you right now, but asynchronous behavior is life, right? Two runners running, we don't run at the same speed. Cars driving, I mean, so in digital electronics, asynchronous things are just sort of a natural behavior that we have to represent. And Doppler and SATCOM is a big reason why that happens. Is Doppler frequency, I mean, this is a guy I used to work with at the other company. He said Doppler frequency is not proper to understand what's going on when two platforms are moving at different velocities. It creates a Doppler frequency, but he said fundamentally, and I agree, it's the time axis is actually changing. It's either getting more compressed if they're coming together, or it's stretching out if they're moving apart. So all the clocks in a system, whether it be the carrier frequency, that's impacted the most, but then as you come down, there's still warping of the time axis, most noticeable at the gigahertz frequencies of radio communications. So the book says, yeah, we could sample a signal and then we convert it back to analog and resample it at a different rate. That's kind of nonsense, but that's just showing you that kind of a wide open area that came along in digital audio, which kind of preceded RF, I think, digital signal processing, is that 44.1 was chosen for the compact disc, and then the studio audio processing established that they would use 48 kilohertz, or 2 times 4896, or 4 times that, 192 kilosamples per second for their sampling rates. So just 48 versus 44.1, how do we get that to go? Suppose the studio recorded the musicians at 48, they're going to mix it and put it on a CD at 44.1. They have to have a rate conversion in there. So it might be, so we'll have 44.1 over 48.0 as a ratio of integers. How do you do that? That's the section, we'll get into that too. So at any rate, how do we reduce by sampling integer factor? That's called decimation. So the factor is m. So the digital waveform that's been decimated is x of n, and it's taking every mth sample of x of n, or back in the analog domain, the far right side there would be every mth sample relative to cap t of the analog waveform. So just the downsampling operation itself is called a downsampler. Usually when it's called a decimator, it generally means there's a filter on it along with it, but our guy from the Army is no longer in the class. If I was going to say, what does decimation mean to him, like if you're a buff of history and wars, what does decimation mean? Say the other side's, well, yeah, you were in the Army, right?
Yeah.
What does that mean to you? What's that?
I was in finance. I didn't do any of this stuff.
Okay. But back historically, if you say the Army was decimated, what should decimation mean? The word deci. But reducing by a factor of 10, I believe, right? Because deci is 10. So decimation would say if your Army had 100 in it, now it would have 10. Is that right? Yep. Ever been to any Civil War battle sites in the country on the East Coast? It's devastating what happened there. I mean, around the world, there's been a lot of wars over the years.
In Virginia, I went to the Air and Space Museum. They have
By the airport?
Yeah, they have the Enola Gay on the display there.
Okay.
That's the one.
I was there last year with my family to that museum. That was our stop before we went to the airport to fly home.
We did too.
Oh, really?
For the airport, yeah.
Yeah, it's a very nice place. It's part of the Smithsonian. And I saw satellites on the ceiling of TDR's satellites and some other things that I've been worked on. So if you like that stuff, it's pretty cool. So this is decimation may mean by 10, but for us it means M, decimate by M, and it's a misnomer then. Engineers, I guess, probably created this, right? Because we're not good in grammar. Downsample by M, maybe is better terminology. So we have to look at what happens with the spectrum when we downsample by some factor of M. So we come along and we're going to tie back to the analog signal spectrum, XC, and what we're going to do is we're going to replace, that's going to be replaced by T prime, and that means it's going to be that. So inherently that says if we're downsampling, we're going to have, what's going to happen? If the translates were spaced at some interval like this, and now we downsample by M, what I think of if a larger number is in the denominator, as we sweep omega with a larger denominator, have you ever done printing with an ink roll where you're rolling something out on like printing? I'm trying to think. It was something I did as a kid that I can't remember, where you would have like a roll that would have ink on it and you can roll something out. And if you make the roll smaller, it's going to spin faster, so the images are going to occur quicker, and if it's bigger, they're going to be spaced out more. So now we're making effectively the diameter of our roller smaller because we're dividing by M, so it's going to make everything compress. It's going to contract it. So the images that were rolling out spaced nicely are now going to be smearing over each other. So what the book does is it tries to get you to understand what's happening mathematically when you put this M in here as opposed to just T. It says the replicas in the decimated signal are replicas of the analog signal with the MT placed at all multiples of 2 pi, while in contrast without it, they're at 2 pi spacing. So it's going to change the spacing now to 2 pi over M. And what you can do is make it as a, if you take into account the inherent periodicity of the e to the j omega, you can write it out as just M replicas of the compressed signal. So what I want you to get is the concept of what's happening, not try to see through the mathematics, because it's complicated. It's not calculus, it's just simply saying the visual idea is what matters. You're going to be taking and compressing these together more, and they're going to occur over and over again, so you still always have in the discrete time frequency domain periodicity. You have period of 2 pi, but you might have more cycles of that, and that's what this is telling you. You have M cycles of that repeated, or M copies. So I was just saying, this is always true. So with downsampling, the potential for aliasing exists, and if you ever are having a cause for a pause in your brain, like, does that make sense to me? If you take less samples of the underlying analog signal, what's going to happen? You have the potential to misinformation because you're going to not grab everything. And that's exactly what aliasing means, is that something is not what it appears to be. It's now an alias. I mean, the same idea in, I I just had to renew my passport last week or 2 weeks ago, and I got it in 2 weeks' time, which was amazing. After I renewed it, they ask you what are your aliases, right? Or I saw in the news yesterday some rock musician, was it Ozzy Osbourne, was shot in Nevada or something. But I didn't know that much about, I know who he is, but I didn't realize they listed his real name, and then they listed he has like 3 aliases. So maybe some of you have aliases. I don't have a need to know, but you know, that's possible. I mean in your names. I don't mean your double though, but or your alias person. But so here's a simple example, and we'll look at this, and then we're going to move into the review time. So m is equal to 2. So we just start off this one easygoing with 2, and we plot the spectrum of this, plotting it looking like there's no aliasing, well separated. And then we put in that factor of 2. So we first go to the discrete time axes with that. So we go to the little omega axes, and then when m is equal to 2, I didn't dwell on that, but there's a 1 over m in here. So, and there's an mt scaling factor. So when we alias, when we downsample, we take less samples, so the scale factor here, rather than being 1 over t, is 1 over mt. Important for working homework problems. And then we think about the act of compressing. So the compressing relative to the new axes is actually stretching it, and it has to do with the way the axes are scaled. So I was saying they're compressing, but the axes, omega axes, actually looks like it's compressed. So if we were, pi over 2 was our cutoff frequency for our original analog spectrum. When we alias by a factor of 2, that now moves over to pi. It's just a matter of the way the axes compression action is working. So I think maybe I said something backwards about the wheel. It's rolling out slower if you look at it as the inverse. I probably messed your minds up for the rest of your life now. It has to do with the fact that if we sample at half the rate, a normalized frequency of pi over 2 is now going to be at pi, just because of the fact we're sampling at half the rate. So they stack up like that, and you go back to the omega domain, we can see that everything lines up shifted. That's another thing that you should do, which James got to do a little bit of in the lab, play with an audio signal. You can play it back faster or slower, and what happens? If you don't adjust it, the pitch shifts automatically. What time is it? It's late. It's late today. There we go. The AV department guy asked me, so what do you do when you restart the projector? I said, I put my finger on the button after a pause. I really think it's something to do with the power control in here, but the lights didn't go off. I don't know. At any rate, it's back again. So in this case, we were good. We didn't have aliasing, although we used up our guard band. We had a guard band in here. Now we've taken it away because of the way that example has worked. In the next example, it changes it and aliasing occurs. So the thing to remember is pi over m. So omega n has to be less than pi over m so that when you decimate by m, you don't cross the pi value in the axes. And I said I wasn't going to go back to Python, but I'll just let you know I still have to do the bandpass sampling too. I have a nice function that's available in the SIGSYS module. It's called downsample, and you just put in the factor of 2. You can actually put in a third argument, and this is kind of what MATLAB does, where you can choose which phase you want of the signal, whether you want 0 or 1. If you're decimating by 2, you could take 0, 2, 4, 6, 8, or you could take 1, 3, 5, 7. So you'll be playing with this. You'll be playing with this in the first project a lot. If you're worried about, confused in how you're going to learn this better, you're going to work a problem in the first project where you're going to be tracking signals and trying to just get your feet on the ground. That, to me, that's the best way. Just do it. Look at the spectrum to see what's happening, and you can look at the waveform, maybe do some filtering. You're going to do enough stuff that I think is going to convince you it's for real and it's really there. Does that make sense? Because I do this all the time in what I'm doing. I build something, and I build a model, I look at the math model, and I try to make the two of them line up with each other. And I'm a hands-on oriented person, visual person, so I like to see things working. If you just throw me the math, I might not be able to conceptualize it until I actually try it. Don't try it, don't try it while driving or, whatever. Don't kill yourself in the process. Okay, so let's go look at the web page. Okay, the basics are what's going to happen before we get into the quick review here is we're going to stop class at 9 a.m. I'll let you have 15 minutes break if you need to go get an energy drink or whatever you want to have. You'll have enough time to go do that. We'll start at 9:15. You'll have till 10:40, so that's an hour and 35 minutes, or 25 minutes, I guess it is. So that's how much time you'll have to work the exam. It'll be with your crib sheet, which I assume you're going to have. I don't think I'll even bring extra copies, so will you have it, or do you want me to try to remember to bring some copies of myself if you need them? You can write notes on them if you want to, too, but you also are allowed a 1 2-sided page of your own notes, and I'll ask you to turn that in. The exam will be 5 pages. It will be just like the ones we're going to go look at. So I have a 2019 and a 2022. I didn't give you 2020. I was on sabbatical in 2021. So let's get that one up, and while we're at it, get this one up. Oops. So exams are always 5 pages, like I said. Sometimes there'll be 2. Normally there's about either 1 problem that's continued per page, multiple parts, or there'll be like 2 problems on a page. That's kind of the flow that I give you. So here, I just had you do some examples with these waveforms in terms of the definitions of time and variance. So I could ask you about causality. Any of those 5 properties, remember this. So this is that type of problem that pertains to the properties. So there's 3 waveforms. So I say find the output in response to delta of n for this particular problem. And I'm saying linearity doesn't hold. So this is the example. This is kind of like that question where you had, well, no, it's not, where you had the systems, the black boxes, you don't know what the system is, so you're just trying to come up with a counterexample. So here, you're looking at, if linearity doesn't hold, if linearity it holds, you can't assume linearity it holds. So, but if time invariance holds, what can you do? If time invariance holds, you can shift the input back and forth on the time axis, right? But you can't form linear combinations of these waveforms to get a specific output. So, which input would you want to use to do that? There's only one input that would be like a delta function. That would be the third input, right? So all I have to do is shift this back to the left by 3 samples, 1, 2, or 4 samples. So that's how I arrived at what the output would be, just using the fact that I could use time invariance. And then the second one, can you show anything about linearity? So I just picked a couple of examples. How could you do that? Well, if it's time invariant, what did I do for my example? There's more than one way of getting a counterexample. I said y1 minus y2. So if I could subtract x2 from this waveform, I should have just a single delta. And then if I subtracted this output from this input, from this output, it should be similar to this output, just with a time shift. Does that make sense? I'm looking to see if linearity possibly could hold, and in this case, I do that and it doesn't. So I've formed a counterexample. Second part of this problem was just plotting a waveform, just getting you used to the idea of flipping and shifting. You didn't have to do any convolution sum, you just had to flip it over. So, but I put also a step on there that's time reverse, so I added a little bit of twisting to that to kind of twist your brain a little bit. But still, you can just review these though and get the idea of the types of questions I could ask. Which one? I mean, rather than a step? Yeah. Because that's what the action of multiplication by delta does. It sifts out just one value, one functional value, wherever the delta turns on. So in this case, this shuts off. When n is greater than 2, this becomes negative. So when n is greater than 2, this becomes negative, which means that it won't let any of this waveform come through. And this is the waveform backed up by one sample. So the key here is that nothing happens at greater than n is equal to 2, and that's going to be with this shifted over by one sample. So these last two values go away. I don't know, my intent here was not to try to go through in intimate detail. So here's the classical solution to the difference equation type problem. This one is a little bit maybe more rigorous, and I know from grading papers that only one person attempted classical solution of difference equations. The rest of you chose Fourier transforms or something like that. So I'm probably not going to try a problem quite as complex as this, but I could try one that I think like was on the other exam that we'll go look at. Here I just set it up for finding what's called the zero input response. So I might do something like that. Zero input response just means that there's no input. So you're just working with a homogeneous response, and the homogeneous response just says that you just solve the difference equation with all of that's going to be shut off. Let's see. Got to get my pencil up here before this will turn on, right? It's not turning on. No, I don't want that. Never mind. I haven't done this for a few weeks, so I thought I could turn my pencil on, but it's not going to work. I don't know why, but at any rate, there's no x input, so that's what I did over here, and I just solved for the coefficients. And I had non-zero initial conditions, so I'm able to just do that. This is a convolving problem, and if you wanted this particular problem, I guess you could have used polynomial multiplication if you wanted to. I just used a direct convolution method to see what the outputs would be by shifting and sliding and multiplying and adding. Just example of Fourier transforms and table entry. Discrete time Fourier transform. In this case, I was using the delay theorem and linearity because I have two shifted step functions in there. Switch to the Z transform. If I was you having to take the exam, I would love to do Z transforms over anything else. True? I mean, I haven't graded your papers yet. I've looked at them a little bit, but it's standard stuff, and you're going to have at least two problems probably from the Z transform, maybe more. So this standard Z transform stuff talks about regions, and then another problem that is inverse Z transforms at the end, just doing partial fraction expansion and solving for the impulse response. The other stuff that's in here, yeah, I think was I don't know why people got low scores on this exam. I think people didn't take the exam. I'm not really sure. Most of the scores, though, except for the ones that were down there 50 and below, and I don't remember anymore what happened, but that's the bundle that matters. So the people that took the exam and could do the exam basically all did quite well on the exam. So don't get worked up about this. I don't even know what these were. They're in here. I didn't delete them, so don't spend too much time looking at that. You're doing the exam problem, right? We'll talk about the histogram at the end. Okay, what's the other one? Fall 2022. Periodic sequences. So suppose I ask you a question on that. You have to establish, first off, that the sequences in there are periodic. So they can be periodic together by finding the minimum period. That's fairly straightforward. Here's a bounded input, bounded output stability type where you're having to use the definition. I could give you one like the homework where you were using the theorem, right? So you'll know if the system is LTI, you just have to find the impulse response, and then you can see if it's stable.
I got a question on that periodic question.
Okay.
You had sine waves, but oh, it's not. I take that.
Okay. See what I did, though, is I put them over a common denominator of 16, and, one was 3 and the other was 5 in the numerator, but n in both cases was 16, and that meant the period was 16. Here I did some modeling in Python, I think, or Julia, I'm not sure which it was at the time. So this is another zero input response kind of a problem, pretty much like the other one. So I might have to look at making this type of problem if I use something like this, not a second order system, so you don't have quite so much work to do. But again, it's solving the homogeneous equation and just using the techniques that were in the notes to get the coefficients. So this is the zero input response again, is what this problem boiled down to. I don't know, I'll be studying that. I have homework to do too, come up with some questions. I do have a lot of old problems, but Here's one that's an example of a theoretical calculation where I said, if we know that we have real and even, I've just asked you to prove that you can compute the Fourier or the inverse Fourier transform more simplistically. So I just took advantage of some properties of sine and cosine, and you're just going to the definition. So this required you to go to the definition and just work it through. I think I have another collection of problems like this. So I may very well give you something like this where you have to just do something different. And this is a Fourier transform theorem problem. It's using frequency translation and just having you draw some pictures. I like this one. I mean, I like things like this where you're actually sort of doing multiple things, but there will be something with Fourier transform theorems, and what is it going to be? I don't really know exactly, but. And then I just put a filter on there that is a low-pass filter, I guess it is. So that you just sketch that out. And if you can't tell, I gave you all the places to do your sketching, so all you had to do was fill it in, and I will be doing things like that. I will do a lot of that groundwork, because that way you have to follow my instructions and I don't have things scribbled all over the place. I want it to be kind of nice and easy to follow. Region of convergence discussion, like that in class, and then some systems in cascade, just multiplying H1 times H2 and doing some cancellation and doing a frequency response calculation at DC and doing the inverse Fourier transform just in terms of frequency response is what this was. It involved putting the system together, but then you were supposed to find the response at omega naught equals 0.4 pi when you put a cosine in at that frequency. This is kind of similar to a homework problem, though, because the input is 10 plus cosine. Another energy calculation type of problem using Parsifal's theorem. That's on your table sheet. But it also, this involved geometric series, so. And there's one other. It's not displaying yet. Okay, it's finally going to. So this is just inverse E transform with partial fraction expansion, pole zero plot, regions of convergence. Yeah, there's absolutely going to be at least one problem like this. There will be actually two problems that involve the use of the Z transform. I'm pretty certain of that. If you've got questions, and we're out of time now, start using Slack more. I mean, I'm watching it and I'm seeing essentially only this guy here has Slack messaged me. Well, I guess two of you have, but just use it. I mean, it's there. I'll try to communicate with you as we move along, but I don't have much to say unless you have something to say. So if you ask a question, I can put it on the open channel. If I don't want to do that, I cannot do that. If you want to post something on the open channel to get comments from somebody else, go ahead and do it. I mean, that's why we have it. So, but you can go one-on-one to me, and then I'll try to respond. Okay, I'm going to stop because people are trying to come in.